we only escape from it by incessantly intercalating new terms between the terms already distinguished, and this operation must be pursued indefinitely. We might conceive that it would be possible to stop if we could imagine an instrument powerful enough to decompose the physical continuum into discrete elements, just as the telescope resolves the Milky Way into stars. But this we cannot imagine. It is always with our senses that we use our instruments. It is with the eye that we observe the image magnified by the microscope, and this image must therefore always retain the characters of visual sensation, and therefore those of the physical continuum. Nothing distinguishes a length directly observed from half that length doubled by the microscope. The whole is homogeneous to the part, and there is a fresh contradiction, or rather there would be one if the number of the terms were supposed to be finite. It is clear that the part containing less terms than the whole cannot be similar to the whole. The contradiction ceases as soon as the number of terms is regarded as infinite. There is nothing, for example, to prevent us from regarding the aggregate of integers as similar to the aggregate of even numbers, which is, however, only a part of it. In fact, to each integer corresponds another even number, which is its double. But it is not only to escape this contradiction contained in the empiric data that the mind is led to create the concept of a continuum formed of an indefinite number of terms. Here everything takes place just as in the series of the integers. We have the faculty of conceiving that a unit may be added to a collection of units. Thanks to experiment, we have had the opportunity of exercising this faculty and are conscious of it. But from this fact we feel that our power is unlimited, and that we can count indefinitely, although we have never had to count more than a finite number of objects. In the same way, as soon as we have intercalated terms between two consecutive terms of a series, we feel that this operation may be continued without limit, and that, so to speak, there is no intrinsic reason for stopping. As an abbreviation, I may give the name of a mathematical continuum of the first order to every aggregate of terms formed after the same law as the scale of commensurable numbers. If then we intercalate new sets, according to the laws of incommensurable numbers, we obtain what may be called a continuum of the second order. Second stage. We have only taken our first step. We have explained the origin of continuums of the first order. We must now see why this is not sufficient, and why the incommensurable numbers had to be invented. If we try to imagine a line, it must have the characters of the physical continuum. That is to say, our representation must have a certain breadth. Two lines will therefore appear to us under the form of two narrow bands, and if we are content with this rough image, it is clear that where two lines cross, they must have some common part. But the pure geometer makes one further effort. Without entirely renouncing the aid of his senses, he tries to imagine a line without breadth, and a point without size. This he can do only by imagining a line as the limit, towards which tends a band that is growing thinner and thinner, and the point as the limit towards which is tending an area that is growing smaller and smaller. Our two bands, however narrow they may be, will always have a common area. The smaller they are, the smaller it will be, and its limit is what the geometer calls a point. This is why it is said that the two lines which cross must have a common point, and this truth seems intuitive. But a contradiction would be implied if we conceived of lines as continuums of the first order; that is, the lines traced by the geometer should only give us points, the coordinates of which are rational numbers. The contradiction would be manifest if we were, for instance, to assert the existence of lines and circles. It is clear, in fact, that if the points whose coordinates are commensurable were alone regarded as real, the incircle of a square and the diagonal of the square would not intersect, since the coordinates of the point of intersection are incommensurable. Even then we should have only certain incommensurable numbers, and not all these numbers. But let us imagine a line divided into two half-rays, demi-droites. Each of these half-rays will appear to our minds as a band of a certain breadth. These bands will fit close together, because there must be no interval between them. The common part will appear to us to be a point which will still remain as we imagine the bands to become thinner and thinner; so that we admit as an intuitive truth that if a line be divided into two half rays, the common frontier of these half rays is a point. Here we recognize the conception of Kronecker, in which an incommensurable number was regarded as the common frontier of two classes of rational numbers. Such is the origin of the continuum of the second order, which is the mathematical continuum properly so called. Summary. To sum up, the mind has the faculty of creating symbols, and it is thus that it has constructed the mathematical continuum, which is only a particular system of symbols. The only limit to its power is the necessity of avoiding all contradiction, but the mind only makes use of it when experiment gives a reason for it. In the case with which we are concerned, the reason is given by the idea of the physical continuum, drawn from the rough data of the senses. But this idea leads to a series of contradictions, from each of which in turn we must be freed. In this way we are forced to imagine a more and more complicated system of symbols. That on which we shall dwell is not merely exempt from internal contradiction, it was so already at all the steps we have taken; but it is no longer in contradiction with the various propositions which are called intuitive, and which are derived from more or less elaborate empirical notions. Measurable magnitude. So far we have not spoken of the measure of magnitudes. We can tell if any one of them is greater than any other, but we cannot say that it is 2 or 3 times as large. So far I have only considered the order in which the terms are arranged, but that is not sufficient for most applications. We must learn how to compare the interval which separates any two terms. On this condition alone will the continuum become measurable, and the operations of arithmetic be applicable. This can only be done by the aid of a new and special convention; and this convention is, that in such a case the interval between the terms a and b is equal to the interval which separates c and d. For instance, we started with the integers, and between two consecutive sets we intercalated n intermediary sets. By convention we now assume these new sets to be equidistant. This is one of the ways of defining the addition of two magnitudes. For if the interval AB is by definition equal to the interval CD, the interval AD will by definition be the sum of the intervals AB and AC. This definition is very largely, but not altogether, arbitrary. It must satisfy certain conditions, the commutative and associative laws of addition, for instance; but, provided the definition we choose satisfies these laws, the choice is indifferent, and we need not state it precisely. Remarks. We are now in a position to discuss several important questions. 1. Is the creative power of the mind exhausted by the creation of the mathematical continuum? The answer is in the negative, and this is shown in a very striking manner by the work of Dupin-Raymond. We know that mathematicians distinguish between infinitesimals of different orders, and that infinitesimals of the second order are infinitely small, not only absolutely so, but also in relation to those of the first order. It is not difficult to imagine infinitesimals of fractional or even of irrational order, and here once more we find the mathematical continuum which has been dealt with in the preceding pages. Further, there are infinitesimals which are infinitely small with reference to those of the first order, and infinitely large with respect to the order 1 plus e, however small e may be. Here then are new terms intercalated in our series, and if I may be permitted to revert to the terminology used in the preceding pages, a terminology which is very convenient, although it has not been consecrated by usage, I shall say that we have created a kind of continuum of the third order. It is an easy matter to go further, but it is idle to do so, for we would only be imagining symbols without any possible application, and no one will dream of doing that. This continuum of the third order, to which we are led by the consideration of the different orders of infinitesimals, is in itself of but little use and hardly worth quoting. Geometers look on it as a mere curiosity. The mind only uses its creative faculty when experiment requires it. 2.